So we're going to start with separable differential equations. Again, this is something that we did look at last year. So the idea is not crazy, hopefully, to you, because you've seen it before. A separable differential equation can be rewritten in this form. F of y dy equals g of x dx. Basically, if we can get all the functions in terms of y on one side and all of the functions in terms of x on the other side, then it is separable. We can only move things by multiplication and division, not addition and subtraction. So for example, if I have the equation dy dx equals x times y, this is separable because I could divide by y and multiply by dx, and I would have all my y's on one side and all my x's on the other. Okay, so this is separable. However, I'm just going to write yes. However, this example, if we had dy dx equals x plus y, I cannot get all my x's on one side of the equation and all my y's on the other side. So this is an example of something that is not separable. It has to be by multiplication by division. All right. The steps to go through solving a separable differential equations, they're very, very simple, the steps. Now, it's within the steps it can get a little messy, but the steps themselves are pretty easy. One, the first thing that we want to do is separate them. We want to separate the x's from on one side and the y's on the other. 2, and sometimes even the separation can be a little bit messy, but we can get there. 2, we want to integrate. If it's going to get messy, this is where it's going to get messy, is in the integration. 3, we want to make sure we have a plus c. Now, the point for this plus c is that we may want to solve for this, depending on if it's an initial value problem. So if we have an IVP, then we're going to solve for that. I can zoom in, I'm not sure it's. And then fourth, we're going to solve for y, and I'm going to use the term y loosely because we're going to solve for that dependent variable. The goal is to get that dependent variable by itself. So we're going to solve for y. Now, you want to be aware of what the problem is asking because sometimes the dependent variable is not y, sometimes it's x, sometimes it's t. It just depends on the problem. I actually think on our notes everything is y, but I think on your homework you have a couple. Oh, no, it's not.
Do these only work for ordinary differential equations? Or these steps? Or do they work for partial?
It just works for something that's, it does actually work for partial in some situations, but we're not going to look at that.
Are you ever going to look at partials or just?
Uh-huh.
Oh.
But not for first, well, yes and no. Yeah, we might, if we have time. All right. Now, the one thing that we need to be aware of is that differential equations have an interval of validity. It happens to be a range of values for that independent variable where my solution is valid. So, like, we can't divide by 0. We can't have logs that are less than 1, right? Or we can't have complex numbers. So most of the time when we solve a separable differential equation, it will not be valid for all values of x. And we're going to work on the interval of validity for each of these. Okay, I'm going to start us off light and easy with this nice, easy separable differential equation.
Oh, man.
Remember, what is the solution to a differential equation? Another equation, right? We're not solving like x equals and getting a number or y equals and getting a number. We're getting a function. Okay? So, here we go. We ready? Separate. My first job is to separate. Now, when we say separate, when we move our y over to the other side, when we get our y's by itself, take as little baggage with y as possible. Take as little baggage with that dependent variable as possible, because we want all of the main work to be done with the independent variable, with x. Okay, so if I were to separate this differential equation, I would divide both sides by y squared, and then I would divide both sides by dx, multiply both sides by dx, and so we'd get 6x dx. So I'm moving my y to the left side and moving my dx to the right side. Does this step look familiar? Yeah, no? Okay. Yeah. Now I'm going to take the integral of both sides. Let's see. Doing that, if you need to, you could think of this as being y to the -2, if that helps. But I'm going to go up a degree, which would take me to the -1, and multiply by that degree. So -1, y to the -1 equals, the integral of this would be up a degree, divide by that degree would be 3x squared. And the plus c, I'm going to stick on the right-hand side. Now, when you watch videos of this, some people will differentiate their c's. They'll call them C1, C2, C3, then they just keep going. I don't believe that is entirely necessary. There are some differential equations where we will have multiple constants of integration, but we'll see those when we come to them. We don't need it just yet. So I'm going to stick my plus c with the x's. Now, a couple things about that. Really, both sides should have a constant of integration. But what happens? I subtract a constant from a constant and I get a constant. Still a constant. Okay. My goal is to solve for c if it's an initial value problem, which this one happens to be. You do not have to do any work to get y by itself to solve for c at this point. Sometimes it's easier not to. Sometimes you may want to. It's kind of up to you. If you want to get y by itself first and then solve for c, great. If you want to plug in c or the initial value as it is, great. There's really no, you must do it this way. So I will probably plug in here. And if we plug this in, I'm plugging in the 1 and the 1/25th. So I would have 1/25th in for the y variable equals 3 times 1 plus c. So we get -25 equals 3 plus c, so c would be -28. Now, my goal is to solve for my equation. So I have this expression here that is -1 over y equals 3x squared minus 28. But I need to get it in terms of y equals, if possible. This one happens to be possible. If it isn't, you leave it. We'll look at one that isn't. I'm just going to switch this. And there we get our y. Okay, let's talk our interval of validity. Where is this solution valid? Is it valid everywhere on the domain?
No.
Why?
Square root of 28.
We know 3x squared minus 28 cannot be 0. Right? Which means that x cannot be plus or minus the square root of 28 over 3. It's pretty, right? Keep it as ugly as you can. Don't try to simplify this. It's not worth it. Now, here's what that creates. That creates 3 intervals. I'm out of room. Oh, see, I want to just keep that grouped. Hold on. Okay. Oops. I don't know how I switched. Okay, so we have these 3 intervals. And eventually I'm going to hope you get past writing the 3 intervals because we need to talk about them. Mm-hmm. That one solution yields 3 issues or 3 intervals for this function. I may or may not need all 3, but it all depends on that initial value of 1. Where does x equals 1 fall into?
Negative 28, there's no others.
That middle interval right here is the only one I'm concerned with for the initial value given. And therefore, my interval validity for this solution is negative root 28 over... Oh, that's supposed to be all over 3. Sorry. Sorry. That definitely is worse. Okay.
Put it over root 3.
Yeah, that's a good way to do it. There you go. Winning. Therefore, sorry, I don't know how I lost it. Therefore, that's my interval validity for this particular differential equation.
Why don't the other 2 matter?
Because my initial value doesn't fall in those intervals. Good times, right?
Isn't that middle interval only exist because of the initial condition?
Yes. And then it's only valid because of the initial condition.
What's the initial
Because
condition?
the other ones don't matter even though they're based on the initial condition?
Good question.
Let's see.
What if you get your initial condition, you plug it in, you get C, but then when you replug it into your initial condition, it falls in a interval that does not exist. Is that possible?
No.
You solve the equation.
Yeah.
Something didn't go right. Brooklyn, you had your hand up just a second ago.
I think we got it.
Okay. All right, let's try the next one. It's not terrible once you simplify it. So take a second. It's going to be more than a second. Take a second and try this next one. All right, let's just see if we can get this separated first, and then we can move on. Hopefully in separating this...
I just Googled chapter, I Googled naked economics summary by chapter.
Wait,
And it is the first option.
wait, which one?
The first option when you Google.
You can also just not read it. That's what I did. Just don't read it.
Yeah, I didn't read that.
You don't have to read it.
Is it not for
Yeah.
No, it's
Did you guys
I
review
used
these?
these
Like,
two things.
Yeah, but you can just be in all that. It doesn't matter.
I read it too. I can read the rest.
I don't think so.
Okay, I felt like
Certain
that
sections
was
of reading. I just don't have time to read 300 pages.
All right. If we integrate both sides of this, how'd we do?
right when you get 1 or square root is 1 plus x squared.
Yeah.
Okay, yep, I would probably use a u substitution on that right side if that would make your life easier. I know it's been a while since we've done that, so if we let u equal 1 plus x squared, then du equals 2x dx, which means 1/2 du equals x dx, and then I can rewrite this integral as 1/2 1 over the square root of u du. That becomes easier to integrate. for most of us. Some of you are very good at seeing those patterns and can just do it. Great. More power to you. What? And so then we get the square root of 1 plus x squared plus c on that right-hand side. And on the left-hand side, if we integrate that, what do we get? Go up a degree, divide by that degree. So we get y to the negative 2 over negative 2, or 1 over negative 2y squared. I would probably plug in your initial condition here. That would be my preference. I just think it'll be easier. So we get 1/2, negative 1/2 equals 1, the square root of 1 plus c. So c equals negative 3/2. Great.
Oh, I forgot about the root 1. Oh my god. That's what. You know what?
Wait a minute.
Man. Oh, man.
All right. Now, this is where it gets really messy. Because first thing I'm going to do is multiply everything by 2. Or probably negative 2, actually, I think would be easier. 1 over y squared equals negative 2 times the square root of 1 plus x squared plus 3.
You can just take the reciprocal of it all and the square root of that.
Okay, so then we get y squared equals 1 over negative 2 root 1 plus x squared plus 3. And then it'd be the square root of this. Now, we know that when we take the square root, you should be plus or minus the square root. Is there one that is correct over the other in this case? It should be plus or minus. Why? I agree.
If we left it as y squared equals, would that also be fine?
It's a yes and no. Well, we're not doing WebAssign, so I guess it doesn't really matter. Yeah, it'd be fine.
Okay, but how do you get the bounds for that?
Okay. And we're only concerned about, who was it? Was it Sanjana that said that? About the negative?
Yeah.
Why'd you say negative again?
Because y equals -1.
Right, we're going to choose the negative because of what it equals up here, of the negative 1. And then my interval of validity. What would you say? It's ugly to start with. We know that this expression here needs to be greater than 0 because it's in the denominator in a square root. Can't be equal to 0. So solving this, I would get, I'd subtract the 3, divide by negative 2, so I get, and dividing by negative 2 means I flip my inequality sign. So I know it needs to be less than or equal to 3/2. Squaring both sides, I'd get 1 plus x squared is less than 9/4. Minus 1, we'd get x squared is less than 5/4. Square root of that.
Root 5 over 2.
We know x needs to be less than root 5 over 2, but greater than negative root 5 over 2. So this would be my interval of validity.
Oh my god.
That's fun, right?
No. I feel like there's just like the stuff that's crazy, but like
Messy algebra.
there's so many like micro-elegance.
So let's look at this example because it is going to be messy. This is going to meet several criteria because remember in the beginning when I said our steps for solving are great, they're nice and easy. And our goal is to get y by itself, or that independent or that dependent variable by itself. The problem is that is not always possible. When it is not possible, it's called an implicit solution. And when we're dealing with an implicit solution, we do not have to do an interval of validity. See, there's perks. No interval of validity because it'd be really hard to solve for what that interval of validity is. All right. A couple of properties we need to remember before we can separate this, because this is separable. My two variables are y and t. This can be separated even though there is a e to the y minus t. You need to remember, because this comes up, you need to remember this property here. Remember in exponents, if we have x to the a times x to the b, it equals x to the a plus b. It works in reverse as well. Meaning, if I have e to the y minus t, I can actually separate this to be e to the y times e to the negative t. And there's a really messy integration by parts in this one.
Okay, yeah. I got to this separately.
End my life.
I'm finished.
Okay, so let's separate this as much as possible, and then we'll walk through the messy integration by parts. Okay. It is hard. You're in differential equations, people. It was not meant to be super easy.
I was not told that it was going to be difficult.
Is it e to the negative y cosine y dy equals e to the negative t1 plus t squared dt?
Well, yes.
Yay! I did it. I did it. Like, I'm proud of myself. Okay, like one step at a time here.
Oh, no.
God.
What's your weekly goal?
Yeah, your sub isn't going to do
Okay. Did we get this far in separating it? E to the negative y, that would be moving this e to the y over, dividing it. Secant of y, if I'm going to divide by the secant of y, 1 over the secant is the cosine, so this gives me cosine of y dy. So all my y's are on the left-hand side. The e to the negative t stays, the 1 plus t squared stays dt. Move the dt over. Are we okay with that separation?
Sure.
Okay. This has two integration by parts.
You do twice?
Yep, because the left side and the right side. And the right side you'd actually have to do multiple times.
Integration by
What
parts.
do you sub now?
Yeah.
No, U sub won't work.
I'm going to quit.
Oh,
Yeah.
no, 'cause you
It goes back to college algebra. Like,
Okay. I'm going to move to the side real quick.
Oh, that's not fair. You get extra space.
I know, but I'm just going to remind you of integration by parts.
What are you choosing? Like what? It feels like you can choose both.
I don't know if you maxed out.
it's like this
You can. It creates a loop.
Isn't this one the DU or something?
Okay.
You take B and then you find B and you get the derivative of U.
I wonder if we could actually max out the what?
Okay.
Doing like reps like
So the integration by parts is if we use integration by parts when we have a product rule.
You don't use the sus machine?
When we have a product rule, I can set up an integration where I'm going to choose an easy to integrate dv and an easy to take the derivative of u. And I'm going to write this formula, use this formula. Now, here's the problem with this first one on the left-hand side. Think about the integrals or the derivatives of e to some power. It just keeps repeating, right?
Yes.
Think about the integrals of cosine or derivatives of cosine. It keeps repeating as well. Yes. This integration by parts on the left-hand side is the one where it creates a loop, and we actually have to solve for it by getting back to the original problem and then dividing. Right? I'm going to walk you through it because it's been a while. Okay, I'm going to let u be e to the y. So I'm going to do this first one.
Either way, I want to
I'm going to do, sorry, e to the negative y. I'm going to use e to the negative y. I'm going to let u equal e to the negative y. And I'm going to let dv be the cosine of y dy. Remember, we create a table where we work between taking the integral and the derivative.
Don't we have to get v and d first?
Yep, so I'm going to take du, which would be negative e to the negative y. Is that right? Yeah. dy. And v, anti-differentiate that, and the antiderivative of cosine is sine. And what we would do is we would do uv, e to the negative y, sine y, minus the integral of v du, which is negative e to the negative y dy. I'm going to stick my negative out front and make that a positive. Okay, but here's a problem. We're stuck again. Watch this carefully, because remember, we would need to do integration by parts on this one. And I'm going to go through it the same way. I'm going to do u is e to the negative y. Du then would be negative e to the negative y dy. dv is sine of y. So v is negative cosine y. Do you remember doing this? Okay. So we still have an e to the negative y sine y plus, where are you at negative sine y? No, I pulled the negative out and I made the integral positive. Plus uv, now I'm going to go through that process again. So uv would be negative e to the negative y cos y minus the integral of v, negative cos y, I'm going to put plus, dy, v du, and I have another negative, so I'm going to put that negative back out. Good times. Okay. What do you notice?
We're gonna get back. Oh, you already are.
We are back to the start. You should notice that this integral right here is the same as the one we started with up here. Do you remember that? Okay. So remember, we had this integral. This is all equal to the integral of e to the negative y cos y dy. And the whole purpose that I'm going to do now is I'm going to move this to the other side. I'm going to add the integral to both sides. So I end up with 2 times the integral of e to the negative y cos y dy equals, and what I have so far is e to the negative y sine y minus e to the negative y cos y and to solve for this, because the whole point of this is to get this integral. Well, to get this integral by itself, I just need to divide by 2. And so then we get the integral of e to the negative y cos y dy equals e to the negative y sine y minus e to the negative y cos y over 2. How fun is that? Because we've done the left side. No room.
So just, how? Oh, you move that over there and you subtract this, you got 2 of them, and you divide it. And that's what it equals? Oh my god, what are we supposed to do with that thing?
Okay. Well, that's only the right hand or the left hand side of my equation.
Just when you think you're done.
You're done, yeah. But this one looks easier than the other side.
Okay. There is one more side. And this too would be integration by parts. But let's think about it. we talked about a technique with integration by parts that says, if I have a polynomial, do I have a polynomial? Yes, I have a 1 plus t squared. That's a polynomial. If I have a polynomial multiplied by anything else, I would have to do integration by parts multiple times again. Why? Because every time I take the derivative of that polynomial, it's going to get less and less degrees, which is good, but it means I have to repeat the process, especially when the other term is in e to the negative t. Why? Because e to the negative t just keeps going. Derivatives or integrals, it keeps going. So remember, we had a special integration by parts that allowed us to use a table of values, like a table of values. It's not really a table of values. It's just a way to organize your thoughts. Where we take the polynomial, 1 plus t squared, and I'm going to take derivatives of that polynomial until my derivatives get to 0. So the derivative of 1 plus t squared is 2t. The derivative of 2t, 2, that took way too long. And the derivative of 2 is 0. That's the whole point. Get to 0. Get that polynomial to 0. And then what I'm going to do is I'm going to take dv, which would be e to the negative t dt, and I'm going to anti-differentiate it until I get to the 0 part of my table for my derivative. So the antiderivative of e to the negative t is negative e to the negative t. The antiderivative of that is positive e to the negative t. The antiderivative of that is negative e to the negative t. Do you remember doing this?
Yeah,
It's been a while.
This is a lot easier than the other one.
Maybe. Okay, couple things that we need to do with this integration by parts here. My first sign will always be positive, negative, positive, and then negative. Those signs may change based on whatever happens in those derivatives and antiderivatives, but that's how it should start. And then remember, we take and multiply the diagonals.
Then we add the
So this integration by parts would be positive 1 plus t squared times negative e to the negative t minus 2t times e to the negative t plus 2 times negative e to the negative t. So let's good? It could be worse. I don't know. That feels pretty painful. You wish you could zoom in?
Yeah, are we gonna have like or is it just infinity to
Okay. Now, this side of my antiderivative is right here. This side of my antiderivative is right here. So this is my final answer. I have e to the negative y sine y minus e to the negative y cos y over 2 equals, did this have an initial value? Oh gosh, dang it. Here I was thinking I was done. We're not done. It looks so pretty because I forgot the plus c.
I don't know.
Okay, so let's stop for just a second. One, I'm going to scroll up. Maybe a few seconds. Okay, don't scroll up.
Here, let me just scroll up. I can't do anything.
Well, I was trying to zoom and scroll. Okay. Okay. It's real small at the moment.
That was a Bryce level comment.
It sounded like a U level comment because you were the one that made it.
That's fair.
Grant, just. Jag. Jeez.
I feel hurt.
Great.
That was great.
Let's stop for a moment
Thank you.
So like,
and decide, can we solve for y? Not a chance in the world would I be able to solve for y in this one. This is an implicit, how do we get the y by itself? When you've got a negative y as an exponent, a sign, you can't do
you
it.
squared it, then you can make it all.
So the good news, you ready for good news on this problem? No interval of validity. You're welcome.
Wait,
Woohoo.
does that mean it's never valid, or is always valid, or does there?
We
have to
just,
solve
don't
for
care.
C.
we don't care.
This math
too hard to
should
give
be
up.
invalid.
Okay,
And like,
now,
This one's
you would need to solve for the initial condition, which I don't actually know what it is. What did you think it was, Jake?
It's 0, 0, which goes to 5, plus 5 halves on the right hand side.
Plus 5 halves. So there you go. So C would be plus, oh, it is online.
so C would be plus 5, but then everything else doesn't matter. So would we use like a graphing tool to like calculate it?
We would,
We wouldn't.
Like, would we just use that one and then get Y?
no, we would just leave it like this.
So we give up.
Um,
Good job, guys.
what I would love to do is be able to answer some of these questions on block day.
Okay. Are they be all as different as
Alright, time to go frantically study economics.
Yeah, are they all gonna be as difficult as this one, or are they gonna be like somewhat easier?
Because I think so. Did you get 2 over